Welcome to the answer video for the T-pipe from the Spark, a closer look. My name is Dudo and I will show you how to get the answers. The purpose of this exercise is to set up multiple balances to ultimately determine the direction the pipe moves. You can see I already made a drawing of the situation. I took the liberty to rotate the pipe roughly 45 degrees so that the y-axis points up. Okay. So, question 1. To make the mass balance, it is best to take interfaces 1 and 5 together with the pipe walls as the control volume. This is because this control volume contains the whole pipe with all its characteristics, and you only have information about the velocity and pressure at these interfaces. Question 2. Let's put the equation for the general balance. Accumulation is in minus out plus production. Now, this problem is in steady state, so the accumulation term is 0. Also, there is no production of mass within the control volume. The inflow we can write as phi m in and the outflow as phi m out. From this we can see that the inflow of mass is equal to the outflow of mass, so we can write this shortly as phi m. Then recall that we can rewrite the inflow of mass as rho times the volumetric inflow. We can also do this for the outflow, and recall that we can write the volumetric inflow as the cross-sectional area at that point times the velocity at that point, in this case A1 and V1, and on the right hand side we get something similar. Then it is given that A5 is equal to A1. These surfaces are equal, or these areas. So then we can rewrite the right hand side as this. Then we can divide by both sides of the equation by rho times A1, and then we get V1 is V5. So this is what we know about the velocity, that the inflow velocity is equal to the outflow velocity. Question 3. For the momentum balance, you want to choose exactly the same control volume for exactly the same reasons. Question 4. If we have a very tiny particle with a very tiny momentum dp and a very tiny mass dm, then the momentum per unit of mass is simply dp divided by dm. Now we can rewrite dp as v times dm, so we get this, and dm divided by dm is 1, so we're left with the velocity. That's right, the velocity is the momentum per unit of mass. Question 5. For the units of the mass balance or the momentum balance, remember that the production term is the summation of the forces acting on the control volume, and that the units of force are newtons. So all the terms of the momentum balance are given in newtons. Question 6. Let's first put the general equation for the momentum balance in the x direction. This reads as follows: dpx dt, the accumulation term, is equal to the inflow of x momentum minus the outflow of x momentum plus production now. Recall this problem is in steady state, so the first term is 0. The production of momentum is equal to the summation of forces in the x direction. Only forces in the x direction can create x momentum. And then we can also rewrite the inflow of x momentum as the mass inflow times the momentum per unit of mass, and this is the velocity. And then the velocity is the x component of v1, and something similar for the outflow, phi m times v phi x. Okay, so let's write down the equation again. 0 is phi m times the x component of v1, and if you look at the drawing you see that v1 does not have an x component, so this is 0. Then the x component of v5 is simply the magnitude of v5, so we are left with this equation. Then you can also rewrite v5, because from question 2 you know that v5 is equal to v1, and then you have the final answer. Now question 7, we can put down the terms for which make up the summation of force in the x direction. First, the pipe can exert a force on the fluid in the x direction, so we take the x component of Fp on F, and also the pressure can have a force on the cross-sectional area A5, and this will be in the minus x direction, so we write minus P5 A5. Now if we put this in the momentum balance of above, we get 0 is 0 minus phi m v1 plus Fp on F in x minus P5 A5. Now if we subtract P on F in x on both sides of the equation, and we multiply it by -1, we get the following. P on F in x is phi m v1 plus P5 times A5, but recall that A5 is exactly equal to A1, cross-sectional area A1. So these two terms make up P on F in x. Question 8. Recall Newton's third law. The force of 1 on 2 is equal to minus the force 2 on 1. So in this case, the force F on P in x is equal to minus the force that the pipe exerts on the fluid in the x direction. Now we put in the terms for this Fp on F in x, which is phi m v1 plus P5 A1. We rewrite phi m again, as we did before. And you can quickly see that both these terms they must be positive, so that f on P and X must be negative. So it is pointing in the negative X direction. This is in accordance with what we saw in the spark, where the T-pipe moved in the negative X direction. I hope this was helpful to you. If you have any questions, feel free to ask them on the forum. Thank you for your attention.